Okay, guys, the video from class today did not record. It's just stopped on its own. So this is going to be kind of a truncated version of what we talked about in class today, but I think it's a good idea for me to go back and kind of reiterate some of this stuff for you in case you need help with it. And I'm just going to do maybe one or two problems here. We've called this polynomial form or standard form. We talked in the previous video the discrepancies there, but basically what they're going to ask us to do is to put this in a different format. And the way we go about doing that is we are going to complete the square with this. Now, reference yesterday's video to complete the square, but it's going to produce f of x is equal to, I believe it's x minus 3 quantity squared minus 5 then. Okay. And what that gets us, guys, is and just let me, to validate that, if you're ever questioning whether you've done that right, there are a bunch of calculators out there that you can Google. If you just Googled CAS or computer algebra system, you should be able to find one. But if I just type in here, expand 2 times x minus 3. And you should be able to do this by hand, but this just might be a little bit quicker. If I just hit expand and then type that in, you can see it does indeed get me back to 2x squared minus 12x plus 13. So we know we've done things right. And this is a useful format because it tells me what my vertex is, okay? Because we're always going off of the fact that with transformations, which we talked about in class today, if I have that as my parent function, that's x squared, and that ordered pair of 0, 0 is my vertex. If I take that 0, 0 and apply these transformations, it's going to move it to the right. Let's do it that way. I can grab that point again. So move that point 3 units to the right and then 5 units down. And my hopes are that you guys recognize that that's going to be concave up because this is positive. So now we've got an understanding of the fact that that number right there and that number right there tell me that ordered pair of that vertex. It's going to be 3, 5. It's always, if I look at this quantity here with the x, and I take the sign with it, okay, it's always going to be the opposite of that sign. So if it's negative 3, it became positive 3 because it's going to take it to the other direction. So if this was positive 3, it would have taken this curve. We're taking the curve that way. So then the vertex would be in the negative 3, negative 5. So it's kind of the opposite of what we're seeing there with that sign there. And then this one is keep the sign the same way. So I should have done that, put negative 5 there. So that's my vertex. The vertex tells me a lot of stuff. The vertex tells me some range information. Okay, along with the concavity, this thing's concave up, so the range is going to start, take that vertical line there. First y value come across would be negative 5. We include negative 5 and we go to infinity. The domain, because this thing is a polynomial, it's going to be all real numbers. The y-intercept we talked about in class, that's kind of maybe the main purpose of having this format is because when x is 0, that goes away, that goes away. So when x is 0, my y value is 13. This format here is also going to help me determine my x-intercepts. But before I do that, let's do decreasing and increasing. Decreasing and increasing. Obviously, we know the parabola is concave up, so this is a minimum value. It's a local minimum. It's actually absolute minimum as well. But the decreasing is going to occur either to the left or to the right of x value being 3. Because it's concave up, decreasing is on the left-hand side, so negative infinity up to 3, and then increasing is 3 to infinity. So those are nice things to know about every function we come across. And the last thing here we're going to be interested in is the x-intercepts. So this thing here, you could go back to the quadratic formula here with that and find your x-intercepts that way, but you're almost there when you do this because you do completing the square, and the quadratic formula is the same thing as completing the square. So I let that be 0 because that's what my y values are 0 when I'm trying to find x-intercepts. I should be able to solve this, add 5 to both sides, divide both sides by 2, and it will eventually get me this. And then we'll square root both sides. So it would look like the square root of 5 has, now I introduced a square root, so it's plus or minus, is equal to x minus 3. Well, now I'd add 3 to both sides, and now I've got my x-intercepts. My x-intercepts, one of them is at 3 plus root 5 over 2, comma 0, and the other one is 3 minus root 5 over 2, comma 0. And now this stuff here, and I showed you in class, I'm going to do it here, but that stuff is enough to effectively graph our function. That's one technique of graphing. Okay, the other technique was to use the transformations that you start with the parent function having points 0, 0, maybe a point negative 1, 1, 1, 1, 2, 4, and negative 2, 4. We could transform those all by moving every one of those points 3 units to the right, stretching all the y values by a multiple of 2, and then dropping every one of them 5 units down. That would work, but we'll find out that it provides the same points and ultimately characteristics that are associated with the increasing and decreasing. I think in class we did maybe another one. Let's see if we got some time here. Let's just jump down to this one here. I think we did in class as well. So again, going through that the factoring process here, the completing the square idea, we'll have f of x minus 49 is equal to 5x squared minus 30x. Divide both sides by 5, so you get 5x minus 49 over 5 is equal to x squared minus 6x. Here's where I start completing the square, so take half of that, which is 3, square it, and get 9. Add 9 there, add 9 over here. When I do that, I get f of x minus 4 over 5. This is 45 fifths. I add that 9 to the negative 49 fifths. And on the right-hand side turns into x minus 3 quantity squared. Okay, multiply both sides by 5. So it's going to be 5 x minus 3 squared. Okay, and on the right-hand side it would be f of x minus 4. Now I want to add that 4 to both sides, so I'll kind of do that here. And now I've got that vertex form. So now I know my vertex is the opposite of negative 3, so it'd be 3, and a y value of 4. It's a vertex. This thing is concave. It's positive 5, so it's concave up, so that's a minimum. My range, minimum value then is 4, so my range is going to go 4 to infinity. The domain, again, is polynomial, so it's all real numbers. We are decreasing and increasing. This is concave down, concave up, so it's going to be increasing first. So from negative infinity up to 3, which is this x value here, it would be decreasing. From 3 to infinity, it starts to increase. 3 is that interchange, so we don't include that. Yeah, I think that's x-intercepts. Okay, so x-intercepts. So this thing's in the first quadrant. The vertex in the first quadrant, 3, 4. It's concave up. It's not going to touch the x-axis, so we shouldn't have any real x-intercepts, but we should still be able to find the zeros. Okay, we get 2 non-real zeros here. Basically, that's by taking this thing here to be equal to 0. Subtract 4 from both sides, so we get negative 4 fifths. Once I divide by 5 is equal to x minus 3 quantity squared. Square root both sides, so I get plus or minus I, radical 4 fifths, equals x minus 3. Add 3 to both sides. Okay, so those are my zeros. They're non-real. I can't plot those on the xy plane, the real axis, the real coordinate plane. That's all the information we need from that. Alternative way of doing this, we'll kind of shed light on it, and we'll talk about it again in more detail on Monday. But through the fact that we have ax squared plus bx plus c here, if we use the quadratic formula to put this thing in the vertex form, we're going to get, and I'll show you this on Monday, something that looks like this. Actually, plus there, I believe, and then this becomes, I think, plus c minus b over 4a. I think it might be b. Yeah, it's b squared. We get that, okay, but what happens is that we call that obviously h, and we call that thing k. So what happens is that the vertex x coordinate is located at, we were talking about it being the opposite of that. If that becomes like x plus 3, then the vertex, the x coordinate of the vertex is at the opposite of that. It'd be -3. So if I had like x plus 3, and this should be squared. If I have an x plus 3 squared, we know that plus 3 actually moves it to the left 3. Okay, so the vertex would be at -3 as an x coordinate. So we find out that x is equal to opposite of b over 2a. And then to find the y coordinate of the vertex, I can just take my function f of x and evaluate opposite of b over 2a. And that will get me what we call here this k, which is the same thing as if I would take 49 minus 900 over 20, okay, which is just plugging those things into that expression there. But doing this, maybe we see that x is equal to opposite of b. So b was -30, so opposite would be 30 over 2a then, so 10. So the coordinate for the vertex for x would be 3. If I plug that back in then, okay, so take that 3 and plug it in here, you get 5 times 3 squared minus 3 times 30 plus 49, okay, so it's going to be 9, 45, so you get 45 minus, 90 plus 49, so it's -45 plus 49, so there's my 4. So my y value becomes 4. So now I've got the vertex being at x value of 3, y value of 4, so 3, 4. All right, so that might be an approach that you want to use to come up with the formula in vertex form if you didn't like the complete and the square process. We know that each one of these is going to be of this format. I'm not sure what that a value is yet, but x, now my h, so this is at 3, so the center is at, or the vertex is at 3, so it's been moved from 0, 0 to 3, so it's been moved to the right. So remember, that's how we show moving to the right. It's been moved up 4, so this is how we show moving up 4. But here's the idea. If that's what my f of x is, I've got this a. If I would expand this, this would be like x, I think it's x squared plus 9x, or plus 6x plus 13 or something like that when I'm done. That's not this thing here. Okay? I would have x squared, like I said, maybe minus 6x plus 13, I think, if you go ahead and do that. I'm not 100% confident. Yeah, that should be right. But that is not what I want, because I want this coefficient out here to be a 5. So I need a 5 here. Okay. Now, it's not as straight as saying that then I multiply this whole thing by 5, because then you see you get 65 and you don't get the 49 here that we want. But I'll put the 5 here. Order of operations, you're going to say you have x squared minus 6x plus 9. You multiply that by 5. And then once you do that and add a 4, it will give you back this thing here. So those are some alternative options for you in regards to dealing with converting something into vertex form. And my hopes are that we can also analyze and talk about, okay, if that's vertex form, then this thing we can decipher where it's increasing, where it's decreasing, and that sort of stuff. Domain range. Hopefully that's helpful. Get this posted as soon as I can, and you can use that then to help you.